Hi everybody. I think I've fixed my screen issue so you won't have to look at that blurry screen any longer. So welcome algebra students to the world of quadratics. We've waited all year to get to this point. I'm so sad that I'm not there in a classroom with you while we do this, but we will do the best that we can. 8-1, quadratic functions. Now, you know we have already done linear. That was the basic 8th grade. This is algebra. A quadratic function is any function written in this form. Y equals ax squared plus bx plus c, where a cannot be a zero. So a cannot be a zero, which would mean 0 times anything would make it disappear. A and B can be invisible ones. B and C can be zeros. So if all you had was y equals ax squared, that would be a quadratic. All you must have is the a with an x squared. Note, remember when we did linear equations? In linear equations, we required that the first difference of the x factors had to have a common difference, and the first difference of all the y factors had to have a common difference. In order to be linear, your first differences had to be a constant rate of change for both x and y. We used some of this knowledge also when we did sequencing. If you go back and look through notes for arithmetic sequencing, geometric sequencing, we talked a lot about first differences and second differences. In a quadratic function, the difference is a little different. In this case, we require a constant second difference for the y values. Remember, the y values are our range. We know it's not the same as our measures of central tendency y value where it's smallest to largest. This is different. This range means your set of y values. Your set of x values, you'll recall, is your domain. So let's look at these differences. Here are my x values, my domain. I have a common first difference. Here are my y values. My first difference is not the same, so it is not linear. Well, let's check. Is it quadratic? Let's do a round of second differences. And the second differences are constant. That means that yes, this is a quadratic because the second difference for y values is constant. Example. Y equals negative 3x plus 20. Is that quadratic? No, it is not, because the ax squared cannot have 0 as a coefficient. And obviously it did because it's disappeared, it's gone. There must be an x squared to be quadratic. This actually is linear. Y equals mx plus b. In purple, y equals 3x squared plus 1. Is this quadratic? Yes. It is all right to have a 0 value for b as long as it's not for a. There is my 3x squared. In green, y plus x equals 2x squared. Is this quadratic? Well, I see an x squared, but I don't have y isolated, so I need to isolate y first. When I do that, I subtract x from both sides. I rewrite it, y equals 2x squared minus x. I have an a. Doesn't matter if I have a b or a c, but I do have a b. So yes, this is a quadratic formula. Let's take a look at this set of data. I can look at all of these coordinates and I can place them into a chart, of course, in numeric value. I am looking for a first difference. Negative 2, 4. The negative 2 is my x, 4 is my y. I go ahead and put all of my sets of coordinates into my table. Here is my first difference of x's. Yes, they are all the same first difference. Here are my y's. the first difference is not the same. Yes, some of the numbers are repeated, but every number is not the same. So let's try second difference. I go down to second difference, and yes, I have a constant second difference. Therefore, yes, these coordinates will create a quadratic function. Let's talk about the graph of a quadratic function. Looks completely different than a linear function. Remember, my linear function had to be a straight line. And yes, straight lines or slanted lines are straight. In this case, I have a curve, and that curve is called a parabola. Odd little name, but that's the name that we associate with quadratics. Some parabolas open upward, some open downward. This one opens down. The only difference between the equations is going to be the value of a, the coefficient of x squared. When written in this form, y equals ax squared plus bx plus c, a parabola will open upward if a is positive, greater than 0. And the parabola will open downward if a is less than 0 or a negative value. In this case, this opens downward, so it clearly has a negative a negative coefficient of the x squared. See if you can tell if the parabola opens upward or downward on each of these. Go slow with me so you don't see the answers immediately. Y equals 4x squared. A equals 4. 4 is positive, so it opens upward. 2x squared plus y, I have to isolate y. So therefore, I subtract 2x squared from both sides of my equation. Y equals negative 2x squared plus 5. A, the coefficient of x squared, is negative 2. And negative 2 is obviously negative, so it opens downward. Function of x equals negative 4x squared plus x plus 1. You might remember from linears, function of x is actually y. Negative 4 tells us to open downward. Now we have the highest or the lowest point of a parabola, and we call that point the vertex or the turning point. So when I look at this parabola, this is where it turns. That's called the vertex. When I look at the one on the right, this is where the curve makes its turn, and that's my vertex. If a parabola opens upward, like this on the left, then the vertex is the lowest point of the graph. If a parabola opens downward, then the vertex becomes the highest point on the graph. These are also referred to then as your maximum, your highest, or your minimum, the lowest. I can have a set of coordinates for my vertex, and I know here that my minimum is actually my y coordinate, my y value, which in this case on the left is 0, and on the right my y value happens to be 5. So my coordinates of my vertex happen to be 3, 5 on the right. We're going to do a lot more with calculating those vertexes and maximum and minimum. This first section is just an overview, an introduction. So how do you find the domain and the range of a quadratic? Well, let's remember that domain is our set of x values and range is our set of y values. If a specific domain is not given, you can assume that the domain, the x values of a quadratic, is all real numbers, infinity. Because keep in mind, your graph, I'm going to flip back, your graph can have x's going as far left and as far right as it may go. As this graph goes down, it'll start to go out and get wider and wider, the same as this one going up wider and wider. And if we go into infinity, the numbers are endless for the domain, the x values. The range, however, the y values, cannot be all real numbers because it's limited by either its minimum or its maximum. When a parabola opens upward, you have a minimum. Y must be greater than or equal to that minimum. And when the parabola opens downward, your y value must be less than or equal to the maximum. I'm going to flip back again. Here was my minimum. I cannot have any y values less than 0. There would be no plots down here. So I cannot have a range that includes values less than 0. And here I cannot have a range that includes values greater than 5 because you will never graph a plot higher than y equals 5. Domain is the x values, range is the y values. I have 2 examples that came out of a worksheet or a book here, but let's just take a look at them. On the left in blue, what I have is a vertex at -2, -4. That means my minimum is -4, my domain, all real numbers, and my range, y is greater than or equal to -4. So let's try one that goes down. My vertex is 2, 3. My maximum is a +3 on this y-axis. My domain, all real numbers. I can go as far as I want on the x-axis. My range, y must be less than or equal to 3. This was only a short introduction, but we are on the road to quadratics. We're going to have a great time with quadratics, so I hope you're ready. Bye now.